Yes. So in the previous class, majorly we had discussed about the topic matrices. If the graph is given to you, how the graph can be converted as a matrix, in which there are two classifications. One is adjacency matrix, one more is incidence matrix. Okay. So adjacency matrix was dealt with the relation between the vertices. Okay. In your incidence matrix, the relation between vertex and then edge. If you are fixing one particular vertex, you will be having the checking out the relations with how many number of edges are incident with that particular vertex. Okay. By the way, you can just insert one for those edges. For the remaining edges, you can directly put as a 0. So that was a major topic which we are discussed in the previous session. Okay. Now we can enter into another topic, that is graphs isomorphism. Okay, see here, isomorphism. Isomorphism is nothing but it can reflect the same behavior. Okay, if suppose if one graph is isomorphic to another graph, means that graph will behave the same properties of that older graph. Okay, then only I can call two graphs are isomorphic. For example, here, if suppose if I just need to say G1 and then G2 are isomorphic, means I need to say some conditions. So here they are given informally, like it has to satisfy one-to-one and then on-to function. So also they are given one more thing. So instead, you can easily check that. Okay, some necessary conditions are there to verify whether both the graphs are isomorphic or not. Okay, usually they will be denoted to isomorphic graphs by using this notation: G1 isomorphic to G2. Okay, sometimes instead they can use a word, they can provide directly check whether G1 isomorphic symbol G2. So that time you should not get a doubt in that, like what is the symbol tries to say. So you have to keep in your mind. Okay. So next, here how we can easily check whether both the graphs are isomorphic or not. See here, first you need to check whether it has both the graphs. That means in V of G1, V of G1 is equal to cardinality of V of G2. So you need to check both the number of vertices of the graphs are same or not. Okay, next. At the same time, you need to check the number of edges. Okay, the number of edges between the graphs should be equal. Third one, okay, here after it has the equal number of vertices with same degree. For example, you may have the graph like this, like if suppose 4 cycle or maybe 5 cycle, in which if you could check maybe for example, if suppose if you have the graph like this, here if you are checking out, here this should reflect the same degree over there in the another isomorphic graph. Okay, here if suppose if you have the degree sequence like 2 comma 3 comma 4 comma 3, means same degree sequence should reflect in the second graph also. That's what they are discussing in this part. Here particularly, more particularly, you can just simply say, for example, if 2-degree vertex is adjacent to 3-degree vertex, means that should follow in your isomorphic graph also. 2-degree vertex is the adjacent to the 3-degree vertex. It should not be the adjacent with 4-degree vertex. So here the concept should be the same by satisfying this kind of properties. Okay, here usually they will be given same sometimes same shape of the graph, sometimes they can give different drawing of that. For example, they can give in another way. You need to check, you need to whether it has the same number of vertices, same number of edges, it follows the same degree sequence. Also one more thing, if it is having a cycle in the given graph, you need to have the same cycle length in the another graph also. Anyway, let us enter into check the first problem. See here, they are given here two graphs, maybe 3 set of graphs. Our task is assigned here to check whether these graphs are isomorphic or not. See here, first I need to check the number of vertices, 1, 2, 3, 4, 5. Yes, here also 5 vertices. Next, after that, you need to check the edges. So 3, 5, 6. 3, 5, 6. Yes, first two conditions are satisfied. Third condition. So I need to check the degree sequence. See here, this is degree 3, right? This is degree 2. This is degree 3. This is degree 3. This is degree 1. So here, uh, uh, always, if suppose if the vertex is having degree 1 means what is the name of that vertex? Can anyone try to say?
Pendant vertex.
Very good. Pendant vertex or n vertex. Very good. Super. If suppose if the vertex is having degree 0 means what is the name of that?
Isolated vertex.
Super. Isolate. Okay. So here it follows the same degree sequence. For example, here degree is 2. Here degree is 3. Here degree is 3. Here degree is 3. Here degree is 1. Okay. See here 2-degree vertexes having adjacent with two 3-degree vertices. See here it follows the condition, right? Next, 3-degree vertex is having connection with 2 times of 3-degree vertex. Hope you can understand that. Next, terminal vertex is having connection with 3-degree vertex. So here, if suppose I may raise one question to you. Okay. Now, can you just try to check whether these two graphs are isomorphic or not?
No, sir.
Yes. No, sir.
Okay, no is the correct answer. Very good. Can you please justify only 1 point in this?
So that right edge has degree 4, sir.
Very good, superb. See here, this vertex is having degree 4. So in the third condition itself, it fails. So I could not call this two graphs are isomorphic. So both are non-isomorphic. But here, it follows in the number of vertices, it follows in the number of edges, it follows in the same degree sequence, also in the cycle wise, like 2, 3, 3. Here also 2, 3, 3 cycle. Next, 3, 3, 3. So that is also, so totally there are 4 cycles. Maybe like 2, 3, 2, 3, 3, 3. So even I can check like this is also one another 2 cycles. So if we could check with the cycle wise, there also it follows the same degree sequence. So but here in the third condition itself, here in this graph, it fails to show the same degree in both the graphs. So that's why I'm just forcefully to say this is not an isomorphic graph of the G1. Hope you have understood the idea, right? Have you understood the concept to verify both the graphs are isomorphic or non-isomorphic? Is it clear?
Yes, sir. Yes, sir.
Very simple one. See here. So by the way, other two are they are given. These two are isomorphic graphs. Okay. So usually, literally, they used to prove like in this manner only. If the question is asked like a 5-mark question, that time you need to specifically mention write separately like degree of, here it is not required to write like this. So you can just simply write like degree of A. So here degree of A is 3. So here you need to check. So what is the 3-degree vertex is there? Here sometimes they can just give in another notations like x, y, z or something like. So in that case you need to denote like degree of or d of A equal to d of x. So something like, so which will of the exact value. Okay, that should follow the same cycle length also. Cycle length at the same time, same degree sequence in the cycle. If you consider as a separate cycle, it follows the correct degree sequence. So you need to present in the proper way, then only it can be considered as a single 5-mark question. So it's a very, very simple problem. So here they can just simply provide maybe 4 graphs or 3 graphs or 2 graphs in which check what are all the graphs are isomorphic. So if the question is asked like that, first your task is assigned there to check number of vertices, number of edges, same degree sequence, and then last one is if you could consider as a cycle, that time also it should follow the same degree sequence. More precisely, you can just say like if one vertex is having degree in the G1 means that should follow in the same G2 also the same degree vertex can be the adjacent. Okay, that should not create one more vertex be the adjacent with the other degree. So that is an easy one. So these are some examples. Okay, so here, okay, see here I can just say one example to you. See here, what they are saying, check whether these two graphs are isomorphic or not. Anyway, here you can just check like separately. Totally here, this is 3-degree vertices, right? This is 3-degree vertex. This is 4-degree vertex. This is 3-degree vertex. This is 4-degree vertex. This is 2-degree vertex, right? So after that, you can just check. It follows the same number of vertices first. 1, 2, 3, 4, 5, 6. Yes, 6. Okay, fine. Next, edges. Will it be same equal number of edges? G and G dash? Yes or no?
Yes, sir.
Okay, very good. Correct. Third, so here if I check degree sequence with respect to the cycles also, listen carefully with respect to the cycles. See here, first let us write the degrees for that. So this is 2, this is 3, this is 4, this is 4 I think. Next, this is 3, this is 2. Next, you can just check. 2 is the degree vertex is having connection with 3 and 4. 2 is a degree vertex is having connection with 3 and 4. So yes, 2 is the degree vertex. So here's something, it follows error in that. Can you just try to understand what I'm trying to say on it?
So 2 is not connected to 3 in the first graph.
2 is not connected. Sorry, in the first graph. Okay, sorry. 2 is having 2 is not connected. Yes, okay. 2 is having connection with 4 and then 4. But here in this graph, G dash, it is having connection, right? Can you understand what I'm trying to say on it?
Yes, sir.
So
Yes, sir.
by the way, here, if suppose if it feels confusion to you, you can just check separately as a cycle. That time you will understand 2, 3, 4. So you need to just fix the cycle is there or not. Okay. Otherwise, you can just start picking the another cycle also 4, 4, 3. So if suppose if there is failed on any one particular cycle, if it is not following the same degree sequence, means in that case itself you can close the topic. Because of that reason, they are not isomorphic. It is a non-isomorphic graph. Also, they are justified here in different manner, like here A dash and then D dash, which are not adjacent in G. Here A dash and then D dash. Here A dash and then G dash. See here A dash and then G dash are both are 3-degree vertices, right? So, but here in your original graph G, 3-degree vertices are connected by an edge. Can you get the point what I'm saying?
Yes, sir.
So because of that major reason, you can just simply justify only one sentence. That is more than enough to say it is not an isomorphic graph. So here what they are mentioning, like both the 3-degree vertices are not connected by an edge, because it is already connected as an edge in the original graph. Because of the reason, I can say both the graphs are non-isomorphic. Is it clear? Have you understood?
Yes, sir.
Okay, fine. So I can proceed further. So there is an alternative method to check that. What is an alternative method? See here, usually to check, that is also another way. You can follow any one of the method, not a problem. If suppose if they are mentioned by using adjacency matrix concept, or if they didn't mention anything like by using adjacency matrix, means you can follow the previous method itself, not a problem. So this is also easy only. So that's your wish. You can follow any one of the whatever the convenient method for you. You can follow that. Okay. So here they are given two graphs. They're asking to check. They're asking to show that both the graphs are isomorphic. See here, first you need to just write the degree sequence in a proper way of G and then G dash. See here, A is actually this is A degree is 2. Next, B degree is 3. Next, C degree is 3. D degree is 3. Next, please stop me if suppose if I'm writing anything is wrong. Okay, so here two remaining all the four vertices are 3-degree vertices. So they are just considered here like first I am going to determine the adjacency matrix for this A of G in the manner 2, 3, 3, 3 in the sequence. Okay. After that, I am going to check the adjacency matrix for the A of G dash. Okay. There also you should follow the same degree sequence when you write in the A of G dash. That means the adjacency matrix of the second graph. So can you just try to say what is the sequence will come for that second graph? Will it be same like A dash, B dash, C dash, D dash, E dash?
No, sir. It'll start with D dash.
Very good, super. So actually here there is one missed. That is this is here one vertex is missed. That is D dash. So here you should start arranging the sequence like D dash, A dash, B dash, C dash, E dash. Okay, you should write in that proper manner. Then you can start determining the adjacency matrix. Then automatically you will get both the adjacency matrices are same. You can just check whether both are equal or 0, 1, 0, 1, 0. Yes. So by the way, you can check with respect to each row, you will get the same answer. If suppose by mistakenly, if you have used from A dash, B dash, C dash, D dash, E dash means certainly you will get a wrong answer. So your answer might be wrong, like because you have wrongly assumed a degree sequence. So always when you are fixed your mind to follow the adjacency matrix means that time you should strictly follow the same degree sequence. Then only you are able to confirm like whether both the graphs are isomorphic or non-isomorphic. Is it
Excuse
clear? Yes, please.
sir, I do not get why to start from D dash.
Okay. Yes, let me explain one second. See here, in your first graph, G, here the degree sequence is in the form like A. I can consider like A, B. It is not a problem. I can even start from B, C, D, E, A, and then say, what I'm saying like here instead of starting like A, B, C, D, E, I can start from B, C, D, E, A. Not a problem. Okay. Here also B, C, D, E, A. Not a problem. But I should follow the same rule, same cycle, same degree sequence in your G dash also. When you try to determine the adjacency matrix for the second graph, that time also you should strictly follow the same degree sequence in the cycle as well in the order. Okay, so that time it is a notable point. Strictly you need to follow. So because here it follows the order like 2, remaining all the vertices are 3. But in your G dash, if we could start from the value A dash, B dash, C dash, D dash, E dash means that time it will say the sequence like 3, 3, 3, sorry, 3, 3, 2, 3. Okay, it will show the order like this. But here in your first graph, you have just construct the adjacency matrix by using this format, right? But here if you could start like this, certainly you will not get the answer in a equal wise. So you should change the position of the D dash as the first one because that's what you followed in the first graph too, right? So by that reason only I have followed here from D dash, A dash, B dash, C dash, E dash. Is it clear?
Yes, sir. Thank you, sir.
Okay. Okay, anyway, before entering into the next one, quickly we can complete the attendance and then we can come back to that.
So can you explain the order?
Sorry, please.
Can you explain the order once more for choosing the adjacency matrix for G dash?
G dash. See here, actually here it was noted like here you can just consider this as a cycle. See here, this is your 2, this is your 3, this is your 3, this is your 3, so this is also 3. So here, if you could consider that, okay, so 3, 2, 3, 3, 3. If we could consider this as a cycle, 3, 3, 3, that is cycle is existing there. That is this cycle. Okay, next 3, 3, 3, another 3. First, you need to confirm that. Next, 2, 3, 3, 3. So that means 2, 3, 3, 3, 2. Okay, so it follows that. So it follows in the same cycle with the same degree sequence order, not a problem. But here, if you could write in the adjacency matrix in the row wise, column wise, that time you have to ensure that you are following the correct degree sequence. That means here only there are two distinct degrees, 2, 3, 3, 3, 3 only. One degree is 2, another one is 3. If suppose if one more degree is existing there, like 2, 3, 4, that time if suppose if you are following here 2, 3, 3, 4, 3 means you can just simply assume instead 3 I may have 4. So the same order should be followed when you determine the adjacency matrix of G dash, like 2, 3, 3, 4, 3. If suppose instead if you have used like 2, 3, 4, 3, 3 means certainly you will not the answer in a same in both the adjacency matrix. So that's why we are forced to use the same sequence order when you try to feed the adjacency matrix. Is it clear?
Okay, sir. Thank you.
Okay, fine. Okay, please fill the attendance form quickly. Okay. Next, quickly you can complete the session. Listen carefully. So here next one is connected and then disconnected graphs. See here, connected, it's very simple definition. See, connected means here you will have the vertices in the graph G. Okay, you need to check only one thing, that is if suppose if I want to travel from one vertex to any other vertex of the graph, if it is possible to take a path between the any vertices, any pair of vertices means then the given graph is a connected graph. If it is not so, then it is a disconnected graph. Let me explain with the example. See here, I can travel from C to D. Yes, certainly yes. Here, I can choose a path like CA, B, D. Okay. By the way, I can travel from D to A, D, B, A. If suppose if the graph is like this, if suppose here I could not take a path between C and D. I could not take a path between C and B. There is an disconnection between the A and then D and then A. If suppose instead I may have the connection with AC or CD means then certainly it's a connected graph. So now because of the reason I could not travel from C to any other vertex, so here this is a disconnected graph. This is a connected graph. Okay. So now can you try to guess whether this graph is connected or disconnected?
Disconnected, sir.
Disconnected. Very good. Super. Because both the graphs may lie on the same thing. Not a problem. But here I should try to choose a path to travel from V5 to, for example, V5 to V5 means I could not travel from here to here, there. So certainly not. So here it is a disconnected graph. Okay. So next. Yeah, let me just explain to you one more thing. Like here, okay. So here V1, V2, V3, V4, V5. First, you can consider this graph like G and then G dash. Okay. See here, first you can try to say whether G is connected graph or disconnected graph.
Connected, sir.
Very good. G dash,
Connected.
G dash.
Disconnect.
Disconnected.
Disconnected,
Okay,
sir.
so this is already said the answer, that is disconnected. Now we can just discuss on those graphs. This is connected, this is disconnected. But here I can just simply try to say this is G1 and then G2. Okay, now can I try to say G1 is the subgraph of G?
Yes, sir. Yes, sir.
What about G2?
Yes, sir.
That is also subgraph. Very good. So if it is a disconnected, at the same time, if those subgraphs are follows the subgraph of the original graphs, means then those subgraphs are called components of G. Okay. If suppose if one graph is disconnected, that means if G dash is disconnected graph, at the same time the disconnected parts, the disconnected subgraphs will behave the property of subgraph property of the original graph G, means those subgraphs can be called as the components of G. Components of G. I hope you can try to understand. Okay, just I can just ask you one more thing, whether I can consider this G3. Okay. Is this a component of G or not? Yes or no?
Yes.
Is this okay now? So because it follows the subgraph property of G, so it can be a component of G. Okay, next. G4. Will it be?
No, sir.
No. Why?
It is not a subgroup, sir.
It is not a subgraph. What is the reason? Correct. Your pointed is correct.
Sir, there is a as in diagonal.
Maybe there is an extra edge between this vertex and then this vertex. That is originally not added, right? So because of that reason, it is not a component of G. Okay, next. Okay, there are some theorems. So already I've told you, it's an open book test. So it's a waste of time to just read the theorems. But if suppose if you are very interested on this, I just share the materials. You can just take a self preparation on that. But the questions will not be asked from these direct theorems. Okay. So anyway, next definition. Planar graphs. Planar graphs here only one point. If in your graph, if suppose if there is no intersection edges, if no two edges are intersected, means then such graph is called planar graphs. For example, here if no, if suppose if there is an edge, intersecting two, if two edges are intersecting, means in that case that graph is called like a non-planar graphs. If no two edges are intersect in the given graph, means such graph is called planar graphs. See here, this is actually planar graphs. Why? Means here this is the, maybe you can feel like this is the intersection intersecting between the thing. It is also to be drawn, instead of this line I can draw like this. Here there is no intersection between the edges, right? So it follows the condition. So there is an adjacency between those vertices. So here this is a planar graph. Planar graph. Okay, I may raise one more question. Will it be planar or non-planar? Always don't assume yourself. Just take the intersection between the edges. So if suppose if you are taking instead crossover, you're allowed to draw like this also, not a problem. Draw like this also, this manner. So now you can try to say the answer whether this is a planar or non-planar.
So it depends if the middle point is a vertex or
No,
not.
no, it is not a middle point. There is no middle point. Just you're having only four vertices, V1, V2,
Sir, then
V3.
non-planar, sir.
Non-planar. Okay, let me draw and then check. See here. So V1, V2, V3, V4. So I should draw the overline between V2 and then V4. So next V1, V3 next. So I should take an edge by connecting V1, V4. Now can you try to say? It's taking crossover, right? Can you try to say whether it is a planar or non-planar?
Non-planar.
Non-planar. Here, even if you could take outline instead drawing the exact intermediate lines, even if you could take a draw like this, that time also you will get the shape like crossover between the edges. So certainly I should try to say this is a non-planar graph. Okay. So anyway, it's your practice. You can just try this graph by drawing out a line, whether it is a planar or non-planar. You can just check later. Okay. Okay. Next. So next question is complete graph of 5 vertices is non-planar. Complete graph with the 5 vertices means, so it can be in the shape like sorry. V1, V2, V3, V4, V5. So now can you try to say whether it is a planar or non-planar? Anyway, it is given as a theorem. It is non-planar. Non-planar. See here, they are explaining step by step. First, they are just drawing all the 5 vertices. Up to this, it is a planar, right? Next, they are extending one more edge. Up to this, it is a planar. Next, up to this, it's a planar, right? Am I right?
Yes, sir.
Okay,
Yes.
but still it is not completed to construct a full K5 complete graph on 5 vertices. Next, so next, if we could draw the last line, that time you will get the intersection between the edges. So they are just actually here it's a very simple theorem. They are step by step. They are just drawing the they are constructing the graph. That's it. So at final case, you will get the intersection between the edges V1, V4 and then V5, V3. Okay, because of that reason, without crossover, we could not draw the complete graph K5. So by this reason, it is non-planar graph. Okay. Have you understood up to this? Is it clear?
Yes, sir.
Okay.